here today, the presentation here today is to Mars and back, Mars sample return. Let's think about, sort of how we are planning this mission, this campaign, really, this group of missions together as a way to bring back these samples. So, of course, if you go to Mars, if you go to Mars today, it is a cold desert, right? On its surface, Mars does not have the characteristics of a habitable environment. It's very cold, much too cold, too dry. Because of the sort of lack of the magnetic field or the global magnetic field, it suffers intense bombardment from different types of radiation, both from the sun and from elsewhere outside of our solar system. There is no known Earth life that could live on the surface of Mars today. These conditions are much too harsh. For example, even at the Martian equator, every night temperatures drop below negative 70 degrees Celsius. Very, very cold, very, very dry. This is a picture, of course, from Curiosity, which is not the mission that is going to collect samples, but this is the one that is in Gale Crater, really exploring a place in the past that we think may have been habitable, a really interesting environment that in the past may have been this way. So Mars was not always a cold desert. And so many of our missions have been seeking to understand, how Mars's surface has evolved over time, what the past on Mars was like. And I think it's really important to show this slide just to recognize in recognition of the fact that Mars and the exploration of Mars, the robotic exploration of Mars, has not solely been NASA or a Russian thing. It's really been an international activity, right? You can see going all the way back here to the 1960s. There were Russian missions, there were United States missions, NASA missions. But as we start moving forward, we start to see there were missions that were happening, that have been happening. You can see in the sort of code here, of course, is the different colors. This red here is the Soviet Union. The blue is NASA. We've got Russia, Japan, China, ESA, India, the UAE, Italy, and Canada. All of these groups are planning these different trips to either fly by Mars, to orbit Mars, to land on the surface of Mars, or to rove on Mars. Unfortunately, you can see all of these red dots. These red dots indicate missions that were not successful, that were lost before they were able to reach the red planet. But as you can see, over time, we've gotten a lot better. We've gotten many more greens than reds as we've gone forward. And it's really important to recognize here that, this has been Mars, and understanding Mars, our neighbor here, has been a really international activity over the past many decades, and will continue to be so. And in fact, Mars sample return itself is an international collaboration. It is a partnership between NASA and ESA. And so as we're planning all of these things, you can see all of these missions here. Towards the bottom here, they show NASA and ESA together. These are missions, there's been a real partnership there. These are missions that we're planning as a group, that we're planning as a partnership, and thinking about how we explore Mars and continue to explore Mars together. So the next slide is a note for me to actually stop sharing this individual tab and to start sharing a different video. So let me try this and make sure this works. I'm going to share a different tab to show you this video. And this video is sort of a video that shows our current architecture of Mars sample return. So it starts with this lander coming to the surface of Mars. And of course, already on Mars is the rover Perseverance. The Perseverance rover has been collecting samples already for more than one Mars year, for a couple Earth years at this point. And so it will be in place when the sample retrieval lander comes close by. The current plan is for the Perseverance rover to actually come up to that lander, take samples off of itself, and load those into this lander, into a particular container there called the Oz, the orbiting sample container. You can see here it's like a tube rack. The cap would go onto the Oz, the whole thing would be sealed, and then this part here we have the nav of Mars is set to nickel. And what happens with the nav is it gets thrown up into the sky, and then it lights in midair and takes off, and it's the first, the first ascent vehicle to leave the surface of another planet. And so as it gets into space, it goes into orbit around Mars. You can see it releases this orbiting sample container. This orbiting sample container then gets captured by this spacecraft, the Earth Return Orbiter, the ERO, that is designed by our partners at NASA. It gets brought into this area where it gets sort of contained safely. The whole spacecraft would come back from Mars, make its way back to Earth, and then as it gets close to Earth, it would release what we call the Earth Entry Vehicle, this EEV. This EEV will then come and land potentially in Utah, where we have a place to bring back all of these samples. And then that would be, the campaign, the Mars Sample Return campaign. Once the samples arrive on Earth, they would then be brought to a place that we would have, a facility that we would have, where these samples would be analyzed, and we would get all of that science out of that. So I'm going to do one quick thing and skip over this slide and go to I'm going to go back to sharing the presentation that I have. And what you can see here, this sort of gives you the full campaign. So as I mentioned, the first stage of the campaign is the Mars 2020, the Perseverance rover. This is on the surface of Mars right now, collecting samples of rock, regolith, and atmosphere. And its job will be to cache those samples either on board the rover or in a location on the surface of Mars for retrieval. Then you'll have the sample retrieval lander and Mars ascent vehicle to retrieve these samples, launch them into orbit. The Earth Return Orbiter would then capture that orbiting sample container and bring it back to Earth safely so that they could be recovered at the landing site. And then you'd have the sample receiving project, the recovery and transport, bring those to the receiving facility. You would do a sample assessment, sample containment, and then some of that initial science. So I'd like to note, of course, that all of this right now is under review. Right now, we are not actually at a point where we have settled that this is, in fact, the campaign architecture. There's still some variables here as we are working on planning and designing all of these missions. But in general, Mars Sample Return would contain sort of each of these elements, right? Collecting the samples, getting the samples off the surface of Mars, bringing the samples back to Earth, and then analyzing them in those terrestrial labs. So why do we think, we've had this incredibly successful robotic exploration program at NASA, ESA as well. Internationally, we've done a lot of great work exploring Mars remotely. But why do we want to bring samples back? And the crucial idea here, right, is that we've got complementary approaches for Mars exploration. When you're exploring the surface of Mars in situ, right, you have essentially the entire planet worth of sample. You have large amounts of sample, but you are limited to the instruments that you've brought with you in order to explore Mars. So if you're thinking about Mars exploration from that perspective, you only have what you brought with you. So we have some incredibly well-equipped rovers on the surface of Mars, Curiosity and Perseverance. They have fantastic instrumentations, but those instruments are limited in, the resolution, the accuracy, the precision that they can make for those measurements, the amount of different measurements they can make. We had to sort of think ahead to what we wanted to do and bring those things. And we can't change anything out. We can't repair any instruments that have issues with them. We're very limited in what we're able to bring. When it comes to sample return, right, we are limited to the amount of sample that we can bring back, but we are unlimited in the instrumentation. Not only are we unlimited in the size of the instrumentation, some of the instruments that we're interested in looking at these samples are the size of a whole building, a very large building. And so we could bring limited amounts of samples to those instruments, make those measurements there. But also sort of in time, right? When you decide to send a rover to Mars, you are limited to the state of the art at that point for when you send it. In fact, you're limited to the state of the art a little bit before, because you have to do testing and make sure that, that all of it's going to work in the environment that you're in. But when you bring samples back to Earth, not only can you make those measurements right away, but you can make measurements down the road as the technologies improve. If you save some of those samples for later measurements, think how we have saved some of the Apollo samples for 50 years before opening those tubes and doing new measurements on them. You're able to sort of design instrumentation to analyze the samples that you have as opposed to the other way around. So these are really, we think about these as complementary approaches. You can take all the sample you have, but limited instrumentation. You can collect data in situ, and then you can also bring the samples back and make those measurements here on Earth. So what about Perseverance, right? We talked a little bit about how Perseverance is the first stage of Mars sample return. So far, Perseverance, actually, you know what? I updated this part of the screen just this morning, but I didn't update this at this point. Perseverance has driven actually almost just under 30 kilometers in Jezero crater. And it traveled further in its first year than any previous rover had. This is actually, you can see, this is where the rover landed. It came down here and explored a little bit here and then made its way back around this crater up here. This is where the first sample cache was deposited, right here in front of the delta. And so this is what we call the crater floor campaign. Each of these little red dots is where a sample tube was collected, or a sample was collected and put into a tube. It did this delta front campaign and explored this edge of the delta, deposited a bunch of samples here, and it's been climbing up the delta here, collected another sample, went around this crater here and continued up this way. And you can see it's been sort of exploring along this edge here as it's gone. And it's about to embark on the crater rim campaign. So it's going to head over this way. This is unfortunately where we lost the Ingenuity helicopter. You can see this is where it is situated at this time. But here is where the rover is, and it's on to explore. This is actually, like I said, this was collected this morning. This is not day because we're on Mars, so we call them sols on Mars. So this is Sol 1298 that it has been exploring, and it's on its way to go further. So we've collected 28 sample tubes and we have 13 more to go. And so you can actually get this latest location if you look up where is the rover, Mars 2020, and this is updated every day. And so you can see where the rover is, where it's been. You can click on each of these links and see a little bit about what each of these samples were. So as I said, one of the most important things, at least from my perspective, that the Mars 2020 Perseverance rover is doing is collecting samples. So this is a video here. I'll show it again. It shows how that percussion drill works, and you can see, as the shadows get longer, as the day goes on, it drills into a sample here. You can see right here where a sample has been sort of abraded a little bit on the surface, so you get a fresh surface to look at. And here is where a sample tube is being collected there on the surface. And so we collect samples and then we put these samples into the sample tubes. And this is not totally complete. This is a little bit behind. But what you can see here is that these are all of the samples that have been collected, from the very first sample, which we collected as an atmospheric sample, all the way through to the last sample that was collected on the 4th of July. There's been at least one other sample that's been collected since then. But I also have put red boxes around some of these. And what these are actually the sample tubes that have been deposited on the surface at that first cache location at Three Forks. And so what you can see here is that for the first little bit, for the first samples that we were collecting, we collected paired samples. So each time we took one core, we actually took another core from the same rock, not the same core, right? They're not twins, they're pairs. And so we collected two. So you can see here Mount Denier and Mount Ganak. These were pairs. These two here, Salette and Coulettes, are pairs. Robin and Malay are pairs. And so one of each of those pairs was taken and then deposited at the surface. Actually, after this last sample was collected, we started only collecting individual samples. So once we had that pair, once we deposited that first cache on the surface, we stopped pairing samples and we collected individual samples as we've gone along. And so what you can see here, this was a regolith sample. We've collected 2 different regolith samples as we've gone on, a number of witness tubes as well. And so here's what this looks like from that first depot. We actually had a community workshop that was open to the entire Mars science community. It was held in September 2022, so 2 years ago at this point. This was sponsored by the MSR Campaign Science Group and worked on, getting a broad scientific input to provide the recommendation, not only to make this initial depot, but also think about exactly which samples would be there. This depot contained one of each shared of those paired samples, and that plan for how exactly to pair the samples, which ones, was part of the discussion as well. So what we did was the preferred version of the sample, as we're thinking of it, the longer of 2 cores. So if you had 2 paired samples and one core was this long and the other core was this long, you would take the longer one and keep that on board. If there was one, for example, where the tube was left open a little bit longer, and there's a possibility that some material may have been lost or whatever, that sample, the sample that had been sealed more quickly, that one was kept on the rover. The preferred version was kept on the rover, and the other of those 2 pairs was deposited here at this first depot. What you can see here is the Amalek sample was about 10 feet away from the rover when this series of photos was taken. It's a composite here. It's actually apparently 368 different images that were stitched together. And so since each of these tubes is about 7 inches long, about 18-ish centimeters, and about 2 centimeters in diameter, you can sort of see this one was pretty close. The furthest one over here, the Melee one here, was about 60 meters away. So this is a great image where you can see sort of all of the samples that we're looking at. So I mentioned in that previous picture of all of those samples that there were some samples that had been collected later that were not included in that composite image of all of the different, the down core images that we were looking at. And one of those samples, of course, and there we go, one of these samples was from this rock here. And so this was sort of right at the edge of one of the units that we were looking at. We talked about this margin unit that's looking into a sort of different rock type a little bit further up the crater rim. But what we see here is this rock. It's called Bright Angel. And this particular feature here is called Chava Falls. There was not only, two sort of abraded patches that we used to look in and look more closely at it, but we also collected a sample here. The sample was called Sapphire Canyon. And you may have heard of this. There was a big, sort of news release about this because it was particularly excited for a particular reason. What we see here is that we saw, in looking at this rock and making measurements with all of the instruments on board the rover, we see clear evidence of water alteration, or organic matter and redox reactions. And so let me go into a little bit more specific here. One of the things that we see here is that if we look at these samples here, these reduction spots here, this is, we looked at this with the Pixel instrument, which does X-ray fluorescence. We interestingly don't see much difference between these sort of redness here and these white interior spots, but these sort of rims here, these have been reduced locally. And when we see this kind of feature on Earth, this reduction is often by organic material, sulfide. These samples here, these black rims here are made of iron and phosphate. And so on Earth, we see this as a process that generates energy for life. And so that's particularly interesting. When we look at this abraded part here, this Apollo Temple abrasion, we looked at this section here, this piece here with Sherlock, which is a Raman instrument that helps us look for organic compounds. And we found a really compelling, very likely evidence of organic material here. And so looking at all of these things together, this is a particularly interesting sample because there's evidence of water alteration, there's evidence of organic material, there's evidence of redox reactions, which again, on Earth fuel life. So all of this is a particularly compelling sample or compelling area for us to study. And we've collected this wonderful full-length core, which also captured some of these reduction spots. So we're particularly excited. I'll show you this next slide that shows exactly sort of where this is in the context. Of course, the rover got a selfie here. You can see right here where that sample was collected. You can see that abrasion patch there, where we can see the organic material. And here's the margin unit. If you look at this picture, you can actually kind of see how the rocks in this section are a bit different than the rocks in this section. And a lot of the rocks in this section have those sort of striped features. I'm going to go back here, have these straight features that when you look at it up close, you can sort of see these veins here. And so all of this has been particularly exciting for us. There's also some interesting features here that look like they're more created by, sort of hydrothermal energy, which is particularly interesting and may be indicative of an energy source or something. But it's an interesting rock overall, and certainly one that we're very excited to get back in order to understand better. So to revisit this whole picture of where the where these samples, this first sample cache, this Three Forks area, and with some sort of why are we doing this? What's the value of all of this? Mars Sample Return is designed to safely bring back scientifically selected samples to Earth. For sort of this iterative process of study, right? We understand one piece, it leads us to some more questions. We want to look at that with a different instrument. We want to think about a different way to explore those samples. That iterative process is really key and fundamental to science. And so iteratively using the most advanced laboratory instruments that will exist, sort of in the coming decade and beyond. MSR will, of course, be our first round trip to another planet, which will help pave the way for human exploration, beyond sort of the Earth-Moon system. And then ultimately, MSR will develop a set of capabilities that were not demonstrated 20 or even 10 years ago. And so we're particularly excited about the promise of Mars Sample Return and what we'll be able to get out of it. And the way we're really thinking about it is, could Mars have been habitable in the past? Did it have life at that point? And is it alive today? It's really important to think about the fact that, very little of our planet has rocks that are as old as the majority of the surface of Mars. And at that time, about 3.5 billion years ago, or older than 3 billion years ago, that was really the time that life on Earth was becoming, sort of taking hold and growing into a lot of the microbial communities, the things that we start to see as the sort of earliest ancestors of life on Earth. And so at that time when life on Earth was starting, that we don't have those records here on our planet, that's exactly the time that most of the rocks on the Martian surface were formed, were deposited. And so we go to Mars as a way to explore those earliest parts of terrestrial planet, rocky planet formation. Think about what life may have been like on our planet at that time. Think about what the environments may have been like and how we think about exploring those places. So I like to show this slide. This is sort of a word cloud for which, from the most recent planetary science decadal survey that was done by the National Academy of Sciences, sort of thinking about the different questions that Mars samples could enhance our understanding, and really, can answer questions relevant to the whole solar system and our place in it. So I want to just give you this piece of information here. All of the pictures that I showed can be available at the raw images. Every picture that Perseverance takes is downloaded here, usually within 24 hours. So you yourself can go and look at all of these pictures, fresh off the rover, basically. This is the way to go to where is Perseverance and see that path that it's on. More information, of course, about Explore with Perseverance can be here. And then one of the really cool features of Perseverance, it actually can take some audio. And so you can go and listen to Mars as well by going to this Mars Sounds. And then the last slide I have here is just a reminder, if you're on X or Facebook, you can see NASA Persevere. You can follow us here for the latest news. And so I will stop sharing at this point and see if anybody has any questions.